Hello, in this video we're going to be looking at the notes for AP Physics C Mechanics Unit 5, Rotational Dynamics. Please remember to pause or rewind the video as necessary. Let's begin. Section 9.1, Angular Kinematics. Well, in order to get into angular kinematics, we should do a side-by-side comparison with linear kinematics or translational is another way to say it. Okay, so first I'm going to begin with an object, this tiny little object right here, that travels along an arc to this point here. Now, if you draw a line from the center of that circle of radius r to that object, you see it also traces out an angle theta as well. The arc length is defined as the path that the object takes, right? It's the slice of the outer edge, a percentage of the circumference, if you will. The units are in meters. Now, angular position theta, that would be the angle through which the object rotates through. That unit is going to be in radians, not degrees. Now, the equation we use to link the translational to the rotational in this case is S is equal to R times theta. Now, translational velocity or linear velocity, that's the rate at which an object's distance along its path increases. The direction is always tangent to the path. So you can see the object is occurring at several points along the arc. The tangential velocity or the translational velocity is always going to be tangent to the path at wherever that object is along the curve. Whereas the angular velocity is the rate at which the angular position, or theta, is increasing. It is how fast you are rotating. Velocity is how fast you're moving. Angular velocity, the symbol which this is referred to as omega, would be the rate at which you're spinning or rotating. The units would be radians per second, and for velocity, they're still meters per second. Tangential acceleration, well, that would be the acceleration that would be tangent to the path. That's the rate at which the object's speed increases. Again, the direction is also tangent to the path, and this is one component of the full acceleration. The other component is what is called the centripetal acceleration, meaning the total acceleration would be tangential acceleration and centripetal. We'll get to more of that in just a moment. The unit is still meters per second squared. If we're looking for angular acceleration, well, this symbol right here was the Greek letter alpha. And so alpha represents the angular acceleration, and that's the rate at which the angular speed is changing, meaning spinning faster, rotating faster, or slower. So this how fast we rotate. Angular acceleration refers to rotating faster or slower. In other words, spinning faster or slower. This is just the overall rate of the spin. The units would be radians per second squared for alpha. Now, for every translational component, there is a rotational counterpart. So let's go ahead and up above, let's comment on some of these. The rotational, so this is translational variables, rotational variables. Well, x's position for rotation, we're looking at angular position or theta. So every time we see an x, we're gonna change it to a theta. V is translational velocity. That is going to be replaced with angular velocity or omega. A is acceleration. That's going to be replaced with alpha, which is angular acceleration. So we're going to be swapping those three variables. Now, time has no direction, so time is still time. Okay, so let's see how all these works. So we have the first one here, x equals v times t plus x naught. Well, x gets replaced with theta equals omega times t plus omega naught. The second equation, v equals at plus v naught, would be omega equals alpha t plus omega naught. The third equation, x equals 1/2 at squared plus v naught t plus x naught would be theta equals 1/2 alpha t squared plus omega naught t plus theta naught. And then in the final equation, we have v squared equals 2ax plus v naught squared. Well, that would be omega squared equals 2 alpha theta plus omega naught squared. Angular acceleration versus centripetal acceleration versus tangential acceleration. Acceleration can always be broken into two components that are tangential and perpendicular to the direction of velocity. The component parallel to velocity is called the tangential acceleration, and it is always tangent to the path. This component is responsible for the speeding up and slowing down of the object. The component perpendicular to velocity is called the centripetal acceleration and always perpendicular to the path. This component is responsible for changing the direction of the velocity. Let's look at these different possibilities. Let's say we have an object that's moving to the right with no tangential velocity. So no tangential velocity. Remember, tangential velocity is all about what helps an object speed up or slow down. So that means we're not speeding up nor slowing down. That means we're moving in a straight line at a constant speed. We also have no centripetal acceleration either, so we're not curving. Now, if we go down here and examine this one, we have no tangential acceleration, but we do have centripetal acceleration. What that means is we're going to move at a constant speed along the path, but we're going to curve due to the centripetal acceleration. In this box here, we're going to examine a situation where we have tangential acceleration, but no centripetal acceleration. Well, the tangential acceleration is helping us to speed up, but because there's no centripetal acceleration, we're not curving and we'll speed up in a straight line. Now, this is tangential acceleration with the velocity. When acceleration goes with velocity, objects speed up. Now, let's say you are having tangential velocity and you have centripetal acceleration. So it's tangential acceleration and centripetal acceleration. That would be this situation here. Well, if that's true, you have curvature and you have an object that's speeding up. And so you have speeding up on the curved path. And it will not be a perfect uniform circular motion, but something that is just a little curved and not perfectly circular. Well, in this last column, we have tangential acceleration going against the object's motion with no centripetal acceleration. So no centripetal acceleration, we're going in a straight line, we're not curving. But if we're going against the velocity, then that means we are slowing down. okay? Whereas in this situation here, we have tangential acceleration against the velocity and curvature due to centripetal acceleration. So you've got the curvature, but notice the curvature is not getting longer, it's getting shorter because the slowing down nature of this, the acceleration is going against the motion. So we're slowing down on a curved path. So if we're to derive these two accelerations, we can derive these from velocity. And we get the velocity vector is equal to the magnitude of the velocity times the direction of velocity. All vectors are written as magnitude times the unit vector direction. Well, let's go ahead and derive both sides of the equation with respect to time. So if I derive velocity with respect to time, well, I get acceleration. That's pretty easy. But if I derive this side here, I'm deriving a product. I'm multiplying the magnitude, a scalar magnitude times the vector direction. So I'm going to have to use product rule. Now, remember product rule, the derivative with respect to, I'll use x as the example here, the derivative with respect to x of functions f times g are f prime times g plus f times g prime. In which case, by using product rule, we can see that the acceleration vector, the total acceleration vector, is become the following. Well, here you've got the derivative velocity, which is the acceleration, in the direction of velocity. So this part here would be the tangential acceleration. Now this part here, it's a little trickier to see it. It's a little trickier to see it, but this is actually the centripetal acceleration. Okay, and here's how we can define that one as well. You see, we have the magnitude of velocity, but in the direction of the acceleration vector, the centripetal acceleration vector, which is always directed towards the center of the path. Now, we know that the derivative velocity with respect to time is going to be omega. And so if we have v, we already know from our earlier, in fact, actually, let me go ahead and back up. Let me back up to the first slide, something I forgot to mention here. I'm going to move these over here real quick. We did mention that the equation that links arc length and angular position is s equals r theta, and the equation that links translational velocity and angular velocity would be v equals r omega, and then finally the equation that links tangential acceleration and angular acceleration would be a equals r times alpha. And in a more generalized way of looking at this, it's the translational variable equals the radius times the angular variable. And that's kind of an easy way to memorize these equations right here. It's translational equals radius times rotational, okay, is how we get that. Now, with that said, let me use that down here. You see, we know that the derivative of this unit velocity vector is going to be, the derivative is going to be omega, and omega itself is v over r. So dv dt is omega, and v equals r omega. So if you solve for omega, that's equal to v over r. So if I replace that, we've got d, the derivative of the unit vector direction with respect to time is equal to v over r. So I would replace that with that, and you can see we get v, which is right here, times v over r, which is equal to v squared over r, which is equal to the centripetal acceleration. So that's how we get this to be the centripetal acceleration. Okay. Now we can also, we can write centripetal acceleration a couple ways. Just recall, we can write it this way. This is the way we wrote it when we were dealing with uniform circular motion in Newton's laws and dynamics. But we can write it in terms of omega as well. See, we know that v is r times omega. So if we square r times omega, we get r squared omega squared over r, and one of those r's cancels. So centripetal acceleration can also be written as omega squared times r. So you have two different equations for the centripetal acceleration. One is the translational velocity squared divided by the radius. The other is the angular velocity squared times the radius. Parametric equations for uniform circular motion, section 9.1. An object lies on a circle of radius r centered at the origin. Now, a parametric equation is just simply not x as a function of y, but x as a function of a third variable t and y as a function of a third variable t. Do keep in mind that you have omega is your change in theta over time. So that means if I solve for omega, or if I solve for theta, theta is equal to omega times time. Well, r cosine theta times r sine theta. That's your x, that's your y. Components, if you will. Now, let the object move along the circle so that the constant angular velocity is omega. Write the expressions for the coordinates of the velocity components, the speed, the accelerate components, and the acceleration magnitude. Well, the position, what we're going to basically do is we're going to substitute theta for omega t using that equation right there. And if speed is equal to r times omega, or omega r, you can write it this way, and a is equal to omega squared times r, like we just got done deriving, then you could write the velocity as all you're doing is just replacing the r. Okay, what you're doing is you're taking this here, the position vector, and you're deriving it. So the derivative of position is velocity, okay? Now, how do we derive r cosine omega t? Well, the derivative of cosine is negative sine. Using chain rule, the derivative of this would be, hold the outside scalar constant along with it, and it would be r the derivative of cosine is negative sine, so negative r sine omega t, but then you have to use chain rule for the inside function omega t, and the derivative of omega t with respect to t would just be omega. So I'm going to multiply the omega times the r out in front, and I get negative omega r sine omega t. That's how we get that there, is just taking the derivative of that. Similarly, if I take the derivative of r sine omega t, well, the derivative of sine is cosine, I get omega r cosine omega t. Now, if I derive this here, I will get the acceleration function. So let me try that. To derive that, the derivative of sine is cosine, so I would get negative omega r cosine omega t. But I've got to multiply times the derivative of omega t with respect to t, which is just omega. And now I've got omega times omega is omega squared times r. And omega squared times r is the acceleration. And you can see I get negative omega squared r cosine omega t and negative omega squared r sine omega t. So you don't have to memorize these. All you have to do is work from a basic idea here and make sure that you know that, of course, the derivative of position is velocity, the derivative of velocity is acceleration. And that will help you be able to essentially derive if you need to. Section 9.2, moment of inertia. Let us define mass conceptually as the measure of how difficult it is to accelerate an object. The moment of inertia would therefore be how difficult it is to change the rotation of an object. The moment of inertia, and by the way, sometimes we will synonymously refer to this as rotational inertia. Moment of inertia, rotational inertia, they will get used synonymously. The moment of inertia of an object depends on the mass the object has and how that mass is distributed. The basic equation for the moment of inertia is kmr squared, where the k in front is a constant, and it is called the shape constant because it only depends on the shape or the basic geometry of the object. Now, let's note some of the possible moments of inertia for various geometries. So let's say we have a point mass m some distance away from some axis of rotation. We would refer to this point-sized mass as a particle. So all particles are things that just simply revolve around other things, no matter the size. And I is equal to just simply mr squared. Now for this one, it's also important to know that I is equal to the sum of mr squared. So if you had, let's say, 4 particles rotating around, it would be mr squared plus mr squared plus mr squared plus mr squared. You add all the mr squared for all the point-sized particles that are rotating around some fixed radius. Now a thin hoop, and we'll derive this in class so that you understand where these formulas come from, but a thin hoop is also I is equal to mr squared. Now a disk, the mass, see the mass distribution of a hoop is all the way at the end. The average mass distribution for a disk is closer to the middle. Therefore, it has less rotational inertia, specifically half, 1/2 mr squared. Now, for a solid sphere, the rotational inertia is about 2/5 mr squared. Okay, now that's, keep in mind, this is for a solid sphere. I is equal to about 2/3 mr squared for a hollow sphere. Now we finally come to a rod rotating through different axes of rotation. If you have a rod that's rotating through its center, I is equal to 1/12 ml squared. No longer r, L is the distance to the radius of rotation, to the axis of rotation. Here you're rotating about the end point of the rod, so I for a rod that's rotating through one end of the rod would be 1/3 ml squared. And again, we will be deriving these equations in class so that you have a decent understanding of where they come from. Section 9.2, Torque and Rotational Statics. The cross product, also called the vector product, is a way of multiplying two vectors. The result of a cross product is a vector. So we can say A cross B, that would be vector A crossed with vector B, is also the same thing as the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. The direction of this vector is given by the right-hand rule. Now, keep in mind that we could also write it a couple different ways. The magnitude of A cross B can also be written as the magnitude of vector A times the perpendicular component, the magnitude of the perpendicular component of B. Or A cross B, the magnitude of A cross B, would be the magnitude of the perpendicular component of A times the magnitude of B. And that's kind of what we have here. When you look at the geometry of this thing, if you look, you can see that the vector A goes this way, vector B goes that way. So if you look at A goes to the right. So if we looked at the parallel component and the perpendicular component of B, the perpendicular component is the one we're interested in. Okay, now geometrically speaking, the cross product is going to be the area of that trapezoid defined by those two vectors. Let us define force conceptually as what gives an object translational acceleration. Torque, thereby, would be what gives an object rotational acceleration. A force causes a torque. The relationship that relates force to torque is torque equals R cross F. Now, there's a couple ways to state this. R cross F is one way to state it. RF sine theta is another way to say it. Now, I'm going to write this equation just a little bit differently. Okay, we can work with this. We can use this, but we can also write it like this. R represents the distance. It's not the radius per se, it's the lever distance. And the lever is defined as the distance between where the force is applied and the fulcrum, which is the point of rotation. F is obviously the force. And this symbol tau would be the torque. So we can write this torque equals perpendicular force times distance. Now, most of the time, the perpendicular force, if you look at the picture here, got a force applied at an angle, right? Well, you've got the parallel component of force, you have the perpendicular component of force. That's the one you want. And the perpendicular force would be F sine theta. So that's where the sine theta comes into play. F sine theta times R, which is the distance, would be another way to calculate torque. So I prefer to kind of write it like this and really just use this. However, R cross F can be handy too for figuring out the direction of the torque. Okay, let's take a look at example 1. While on a crusade in the kingdom of the Raiders of Doom, Indiana Jones encounters a 150 kilogram, 10 meter long plank that lies flat on a cliff edge, where 3.5 meters of the plank are over the edge as shown. Indy, approximately 100 kilograms, walks out onto the plank to retrieve the script for the 5th movie. How far can Indy go from the edge of the cliff before the plank tips over? Well, this is going to be what's called rotational equilibrium problem. Okay, now how do we know it's a rotational equilibrium problem? Well, you basically have this plank right here that is teetering about that point right there. And you can see the plank has the ability to rotate about that point, especially if he goes out far enough. So that makes this the point of rotation. There's our fulcrum right there. Okay, and keep in mind we're going to be going synonymously between different terms here. Point of rotation, fulcrum, pivot point even would be another way to state it. The first thing let's do, realize that torque involves not just forces but distances. But since torques, what a rotational equilibrium problem is a balanced torque problem. Okay, now torques involve forces, so we have to make sure that we find the forces acting on this particular system. And there's two different masses involved here. There's the mass of the plank, 150 kilograms, and there's the mass of the man, Indy. So let's go ahead and draw the forces acting on this. You'd have the weight of the board would come from the center of mass of the board, which would be right in the middle here. I'm going to call this WB for weight of the board. And you've got the weight of the person. So I'm going to call WP for weight of the person. So mass of the person times G. And then we have mass of the board times G. Okay, so we got that. Then we also are given how far the center of the board is from the pivot point. This distance is 3.5 meters. Okay. Now, what I'm going to do, since I'm going to be using this equation right here, I'm going to reference forces as force 1, force 2, etc. So I'm going to call this one force 1, and I'm going to call the weight of Indy force 2. That makes this corresponding distance for this force D1. D1 goes with force 1. And that makes this unknown x here D2. That's what we're looking for. We're looking for x, which is D2. Okay, now, the way this works is that all of the, if this is the plank right here, all of the forces that cause counterclockwise rotation, okay, counterclockwise rotation would be going this way, that would be the weight of the board. The weight of the board would cause counterclockwise rotation. The weight of the person would cause clockwise rotation. And right now, there is no rotation because it's balanced. However, you have two different torques that are being caused by two different forces. So the relationship we use would be that the net torque equals 0, or that your counterclockwise torques balance and equal your clockwise torques. Okay, now you only have one particular torque causing counterclockwise rotation, and that would be due to this force applied at that distance. So this one would be force 1, distance 1, and then the weight of this person times the distance from the pivot would be force 2, distance 2, and that would be our causing our clockwise torque. And we're looking for distance 2. So go ahead and solve the equation for distance 2. And the force applied would be M, mass of the board, times G times distance 1, divided by, now I've got to get D2 by itself, I have to divide by F2. F2 was mass of the person times g, and you can see how the g's are going to end up canceling. So you can really just focus on the masses, not so much the weights. So mass of the board, 150 kilograms, times now I made one mistake, and I'm going to go ahead and clarify that mistake. The distance of the board is not 3.5. It's actually 1.5. And let me clarify that one. The entire plank is 10 meters long. 3.5 meters of it are over the edge. So that means that each little section here is 1 meter. So that would be 1 meter and then 1/2 meter. So distance 1 is actually 1.5 meters from where the weight of the board is being applied. We're going to divide that by the mass of the person. It's 100 kilograms. You can see kilograms cancels. And x, which is d2, go ahead and put that in your calculator for a second. You get approximately 2.25 meters. So he can walk out 2.25 meters and still the board will not tip over. So when objects have the ability to rotate but don't, that is an example of a rotational equilibrium problem, which will be solved by using what are called balanced torques. Example 2. Indy comes across another 150 kilogram plank, which is tied by 2 cords that holding it horizontal to act as a bridge. Indy crosses the plank and at this moment is 8 meters from the left side of the plank. Determine the tensions in the left and right hand side. Okay, so first, let's go ahead and find all the forces that are acting on this particular board. You have the force of the weight of the board, so weight of the board, that's mass of the board times g. You have weight of the person, mass of Indy, mass of the person times g. You've got tension on the left end, which we'll call tension 1, and then you've got tension on the right end, which is tension 2. Now, what we're going to do, what we can do is we need to choose a fulcrum point, okay? In the previous problem, it was easy to figure out where the fulcrum point is because there was an obvious point of rotation. But here, there is no obvious point of rotation. The nice part about doing a problem like this is that torque equals 0 at the fulcrum. So you have to choose a fulcrum if it's not easily determined. So if I want to solve for T2, if I solve for tension 2, I would let the left rope be at the fulcrum. In other words, I would let the fulcrum be here, and what that would do is that would eliminate tension 1 for consideration because there is no torque at a point of rotation. So if I considered this to be the point of rotation to solve for T2, that would allow me to solve for T2, not worrying about T1. So you have 3 torques going on here. Now keep in mind this would be our board that is rotating about that point there. And if you look at our board, by the weight of the board would cause clockwise rotation because it's pushing down. The weight of Indy would cause clockwise rotation because, again, pushing down. But you can see tension 2 tension 2 is pulling up. That would cause clockwise rotation. So when you're doing this, it's helpful to make some notes of that. This causes a clockwise torque. Weight of Indy also causes a clockwise torque. Tension 2 causes a counterclockwise torque. Okay, so the equation we're using is the counterclockwise torque equal the clockwise torques. There's one clockwise torque and there are two counterclockwise torques. Remember, the equation for torque is perpendicular force times distance. Now, don't cancel the G's this time because tension does not have a G, and you only have G's in these two terms here. So don't cancel the G's in this problem. So we've got one clockwise torque, which would be tension 2, times its distance, which we'll call distance 2, I guess. That's going to equal the other two torques, which would be the weight of the board. So you have the weight of the board times the distance of the board plus the weight of the person times the distance of the person. And you're solving for T2. So T2, now the weight of the board would be M times G, so it would be 1,500 kilograms times G, which is 10, times the distance of the board. Now the distance of the board, the distance of that force applied from the point of rotation here is clearly 5 meters. Okay, now we're on the second part, weight of the person. The weight of the person would be 100 kilograms times 10 times 8. Kind of hard to squeeze that in there because Indy's at the 8 meters away from the left-hand side of the board. And all of that is going to be divided by distance 2. You can see that T2 is 10 meters away from that fulcrum point. Okay, so you have about 7,500 Newton meters plus about 8,000 Newton meters, all divided by 10. That would give us about 1,550 newtons on the right-hand side. Now, the opposite is true. If we want to solve for T1, then you're going to let T2 be the fulcrum. So it's exactly the opposite. So now we're going to let this be the fulcrum. This is no longer a force of consideration because torque does not occur at the fulcrum. And now what would happen? This would be our Planck, right? This is our point of rotation, and you can see, oops, back up. You can see that the weight of the board would cause counterclockwise rotation. You can see the weight of Indy would cause counterclockwise rotation. But you can see that T1 on the left-hand side is going up. That would cause clockwise rotation. So we have 2 counterclockwise torques and 1 clockwise torque. So this causes a clockwise torque. Both of these cause counterclockwise torques. Okay, make a note of that. So we're going to go, let's see, tension 1 times distance 1. That would be this torque, this counterclockwise torque here. is going to equal the sum of those two torques. So that would be the weight of the board, mass of the board, times g times distance of the board, plus mass of the person times g, that's the weight, times the distance of the person. And you're going to solve that equation for T1. Let's plug in. Mass of the board is 150 times 10 times the distance of the board. Well, the distance of the center of mass of the board is still 5 meters away, plus the mass of the person is 100 times g is 10. And you can see, remember, our fulcrum is over here now, and Indy is 2 meters away from that point. Divided by the left end of the board is 10 meters away from that fulcrum right there. And we have 7,500 Newton meters plus 2,000 Newton meters. Divide that by 10, and we get approximately 950 newtons. Example 3. A uniform ladder of mass m and length L is propped against a wall so that it makes an angle theta with the wall. The contact between the ladder and the wall is frictionless, but the contact between the ladder and the floor has a coefficient of friction mu. Find the minimum value of mu such that the ladder will not slide. Okay, well, we have some things we need to find here. We've got a lot of concepts going on in this problem, but first and foremost, realize that the ladder itself, if there's not enough friction to hold the ladder, then what does the ladder do? The ladder, the ladder would fall, but as it falls, it would rotate. Okay, you can see how it would rotate. So this problem is much more than just a forces problem. So there's a point of reference that we'll make, and let's go ahead and write it at the top. If the point of rotation, the pivot point, the fulcrum, whatever you want to call it, is unclear, then it can be arbitrarily assigned. And what that tells us is that the torque is 0 at this point of rotation, whatever it is. Okay, now what that means is the horizontal and vertical forces are balanced. In other words, Newton's first law is a concept in this problem, which means total net force in every direction equals 0, and we're going to use that to find friction. But then we have a rotational Newton's first law, which would basically be describing rotational torque, rotational equilibrium, in which case the net torques are equal to 0. And we're going to use that to find the normal force from the floor. So getting kind of ahead of ourselves here, Now that we've kind of identified what the concept is, we know it's a Newton's law-based problem, let's figure out all the forces that are actually acting on this problem. First and foremost, we've got a ladder that is, let's see, 1, 2, 3, 4, 5, 6, 7, 8 units long. So I'm going to draw the weight from the middle, and I'm going to label that mg. Well, then you've got the normal force from the wall. I'm going to call it NW for normal force of wall. Then you've got normal force of the floor. I'll call that N sub F. And then lastly, you have friction, static friction specifically, right, which is equal to mu times normal force. Now, why is the friction pointing towards the wall? Well, think about it. Friction, this type of static friction, is preventing the ladder from sliding this way. Therefore, friction must be acting to oppose that and must be going that way. Now, in order to figure out the mu, in order to figure out mu, we know that Newton's first law would tell us to balance forces. Forces left equal forces right. Well, forces going left would be the normal force from the wall. The forces going right would be friction, which would be the normal force from the wall is equal to mu times the normal force from the floor. Now, the other thing that we know is that forces going up equal forces going down. That would be the normal force from the floor going up is equal to mg going down. So we've got a lot going on here. The problem is we just don't know what the normal force from the wall is. That's kind of the one unknown that's kind of messing the whole thing up. You see, mu is the ratio of the normal force of the wall to the normal force on the floor, which we know is mg. Okay, but we don't know is what the normal force on the wall is. Okay, and that's preventing us from figuring out what mu is. So we're going to pause this particular part of the discussion. And that's why this cannot be just a Newton's law problem. Because there is the ability to rotate, it doesn't actually rotate, but because there's the ability to rotate, it makes this a rotational equilibrium problem as well. And so we not only have to balance forces, we have to balance our torques too. Now, for this one, we're going to have to balance clockwise and counterclockwise torques. So let's revisit this here one more time. I'm going to zoom in on the picture so you can see it. Here is our lever, okay? Now, you only want forces that are perpendicular to that lever, meaning this direction here. Only perpendicular. Now, look at the existing direction of those forces. Okay, you've got this one here. That's clearly not perpendicular. So I'm going to draw the vector components for that. And I'm just going to draw a bunch of blue and gray. Now, if this is angle theta with the wall, and this is a 90-degree angle, I'm going to call this other angle alpha. Now, since this is a 90-degree angle here, that would make this angle theta also, which would make this component NW cosine theta. And that's all I care about. Even though this one is NW sine theta, I don't care about that one because that gray component is parallel to the lever, not perpendicular. I only need a perpendicular lever. So we'll come back to this one in a moment. Let's go down to the weight. Well, the weight would have part of the weight goes this way, and part of the weight goes that way. Again, let's talk about angles. Here's our wall. Here's our, you can see our weight vector runs parallel to the wall. Here's our transversal. That makes this angle here makes this angle here the same as that angle right there. So our angle theta is actually right there. That would make this mg sine of theta. And yes, this is mg cosine, but I don't care about that. I only care about that one right there. So I'm circling the components that are going to make sense in doing analysis in this problem. Okay, now one more. Let's go on to normal force. Normal force is clearly at an angle. But here's the deal. I don't have to, even though normal force would have components that look like this, okay, and even though angle theta would be up here, and this one would be normal force of the floor, sine theta, and yes, that one is actually not going to provide a torque, because here can be our strategy. Ultimately, we're looking for the normal force on the wall, so we have to find and use that torque, which means this end cannot be considered the point of rotation because you're looking for the normal force of the wall. However, this, we already know what the normal force of the floor is. Normal force of the floor balances the weight. That's easy. We don't need that. So we can make this the point of rotation, the pivot. That's exactly what we're going to do. We're going to let the axis of the point of contact to the floor be the axis of rotation. And what that tells us is that right here, the torque is 0. So I don't have to worry about that force. I'm going to go ahead and, the forces are still there, but I'm going to go ahead and delete the components because they don't matter in this part of the problem. They just don't matter. I'm going to let that be the axis of rotation. Now, with that said, ladies and gentlemen, we only have 2 different forces acting here. Now, I'm going to go back to the lever. Here's our lever. Okay. Now, mg sine theta is pulling down on the ladder, while nw cosine theta is pushing up on the ladder. Now, that means if the pivot point is at the bottom, mg sine, if the wall weren't there, would be causing clockwise rotation. That's a clockwise torque. And nw cosine would cause a counterclockwise torque. So you have one of each, counterclockwise and clockwise. So this is causing a counterclockwise torque. This one is causing a clockwise torque. Okay, and that's where we're going to continue the next part of the problem, is rotational equilibrium to find NW, normal force of the wall. Okay, so that's counterclockwise torques equal clockwise torques. Now, what are these torques? Well, remember, torque, in case you forgot the equation, is a perpendicular force times distance. So the counterclockwise torque would be the normal force from the wall times the cosine of the angle. That's the force. And it is a whole distance L away from the pivot point times L. Okay. And we have the other force is mg sine theta, but that one is at the halfway point of the ladder, so the distance from the fulcrum would be L over 2 on that one. Okay. L's cancel, divide away the cosine, both sides, and NW equals mg, sine over cosine would be tangent of theta divided by 2. Now let's go ahead and take this and find our value for mu. We've got the normal force from the wall right here. That's mg over 2 times the tangent of theta. And we're going to divide that by the normal force from the floor, which is just mg. You see the mg's cancel, and we're left with 1/2. Let me rewrite it. Mu is equal to 1/2 tan theta. Example 4. Well, example 4 is adding another dimension to this because now you have a person of mass m who's climbing the ladder. Now, the coefficient of friction, mu, is the same as what we found. So we know that mu is 1/2 tan theta. Okay, and we can use that later on. We want to find the minimum or the maximum distance up the ladder the person can climb before the ladder starts to slip. So let's do what we did before. Okay, find the forces acting on this ladder would be you have the normal force from the wall. You have the normal force from the floor. You have friction equal to mu times normal force. You have the weight of the actual ladder, which is mg, and then you have the weight of the person, which is a bigger mg. Okay, so you got those going on. Now, again, horizontal forces cancel. Let's do the verticals. And again, we're going to make the contact point on the floor be the axis of rotation. Okay. Don't forget to plug in the value of mu that we just found. Okay. So here it goes. Up to the first part, horizontal forces, you have friction going to the right is going to balance the normal force from the wall going to the left. And since friction equals mu times normal force already, that's mu times normal force from the floor. Okay, and forces up going forces down, you've got the normal force from the floor, balance going up, balances the two weights going down. So that would be little mg plus big mg. All right, now let's focus on using rotational Newton's first law as well. So we've got our let me take care of the components again. So since I'm making this be the point of rotation, I am not worried about the torque due to friction nor the normal force. So we only have torque due to the weight, just like last time, the normal force just like this time, but we're adding one more, and that's the weight of this person right here. So let's do those components again. We've got perpendicular component. Remember, this one was n from the wall times the cosine of the angle. That's theta, right? And then you've got this one here, where this is again the angle, and then you've got this little one here, where that is again the angle. And those components were big mg sine of the angle and little mg sine of the angle. Okay, both of those are causing clockwise torques. So you have two clockwise torques, and we have one counterclockwise torque, or one force that's causing a counterclockwise torque. So we have the fact that your clockwise torques, your counterclockwise torques equal your clockwise torques. There are two, there's one clockwise torque, okay, or one counterclockwise torque, excuse me, two clockwise torques. So in the counterclockwise direction, you've got the force, remember torque is equal to perpendicular force times distance. So the force is normal force of the wall, cosine theta times L. Okay, that is the counterclockwise torque. The clockwise torque, there are two of them. It's the weight of the ladder, so mg, little mg, sine theta, times the distance, L over 2, from the halfway point, plus big mg sine theta. But that's going to be distance x. That's what you're looking for. That's the unknown in the problem. We're looking for x. Okay, so what are we going to do now at this point? Well, still a little substitution here and there. So I'm going to substitute for normal force in the wall. That's going to be mu times normal force on the floor, cosine theta, times L, equals, this part didn't change, mg sine theta times L over 2, plus, this part didn't change either, mg sine theta times x. Okay, one more step. Now I'm going to do one more bit. Remember, normal force from the floor was the sum of the weights, right? So I'm now going to substitute for the normal force on the floor. It's just that little guy right there. So now we've got mu times little mg plus big mg times cosine theta, and all of that is times L, and then nothing else changed. The only thing I'm going to do is I'm going to move the x and the L. I'm just going to move them up in front of the trig function. So I've got mg over 2 sine theta plus big mg, oops, sorry, shouldn't have written it like that, little mg over 2, and then this is big mg x sine theta. So we've got to move the L up, but move the x up. Okay, now recall that mu was equal to 1/2 tangent theta. And we're going to substitute that right in there for mu. So let's go down here where we have more room. So in place of mu, let's put in the 1/2 tan theta. Okay, and then we've got the, I'm going to factor out a g. So it's big M plus little m, and then I've got a factored out G cosine theta, all of that times L is equal to mgl over 2 sine theta plus big mgx sine theta. And the reason I factored out a g over here is because you can see now there's a g in every term, and the g will cancel. So that simplify it a little bit. Okay, now what we're going to do is we're left with keeping in mind that tan is the same as sine over cosine. So this cosine cancels with that cosine, and I'm left with sine over 2. So in the front, I've got sine of theta over 2 times, and I'm going to distribute the L to both parts. So I've got big ML plus little ml. Okay, that whole thing is going on the left side. And on the right side, we've got little ml over 2 sine theta plus mx sine theta. There we go. Getting closer. We're trying to solve for x now. That's the point. Well, I think at this point, go ahead and distribute this. And what we would get is we would get big ML sine theta over 2 plus little m L sine theta over 2 equals little m L over 2 sine theta plus mx sine theta. Now this is helpful because you can see those two are exactly the same and they cancel, which is really nice. So now I'm left with big ML sine theta over 2 equals big mx sine theta. Well, you can see masses cancel, sine thetas cancel. What does that tell you? X is equal to L over 2. Section 9.4, pulleys with mass and friction. Okay, if we have pulleys that have uneven masses, we know that the pulley system is going to accelerate like we saw it happen before. The difference was back in doing those type of problems, we let the tension be the same anywhere on the string, same tension. And we were able to get away with doing that simply because the pulley itself had no mass and there was no friction acting on the pulley. So that's not the case anymore. Now we have a string that is rubbing against the pulley, and the friction from the string is causing the pulley to end up rotating. And you now have a pulley that has mass, and the pulley itself has a resistance to rotation. It has what is called a moment of inertia. It has a rotational inertia. Now, the rotational inertia, in this example, we have two masses, little m and big M, where big M is significantly bigger than little m, hang from a pulley with mass mp and radius r. The moment of inertia of the pulley is given by km times the mass of the pulley times r squared. The string from the masses is light and does not slip. Draw the forces acting on the two masses and determine the acceleration of the two masses. Okay, so do what we did before, any Newton's second law problem. That's exactly what this is. This is a Newton's second law problem, which would be what? Net force equals ma, right? Okay, well, it's also a rotational Newton's second law problem as well. What does that mean? Instead of force, the rotational analog to force would be torque. Net torque equals the rotational analog to mass. Now, mass doesn't really measure anything. but mass is related to the concept of inertia. Therefore, mass is analogous to rotational inertia, which is the letter I. And linear translational acceleration is analogous to angular acceleration alpha. So net force equals ma. The analogous equation that you can match letter for letter is net torque equals I alpha. Okay, let's first figure out the force acting on this thing. The forces acting on the masses would be little mg and tension. I'm going to call this tension 1 on the left side. And m1 is accelerating upwards, m2 is accelerating downwards. Now the acceleration will be the same. The tensions may not be the same, but the acceleration still will be because it's all moving as one unit. Now on the other side, we've got big mg, and we've got another tension, which we'll call tension 2. Now, on this other side here, you also have those same tensions pulling down from the pulley. So tension 1 pulls this way, tension 2 pulls on the pulley that way. Now, I'm going to draw my pulley here. Now, tension 1 actually causes the pulley, sorry, let me fix that. Tension 2, there we go. Draw a pulley again. There we go. Here's what tension 1 does. Tension 1 is on the left side of the pulley, and tension 1 causes what? It causes counterclockwise rotation. Tension 2 causes clockwise rotation. But here's the way we're going to address that one. Let's go back to the top. Remember how net force, we used to write that as causing force minus opposing force equals ma? Well, same thing with a net torque. It's causing torque minus opposing torque equals I alpha. Well, this is the causing torque. This is tension 1 relates to the opposing torque. Now, torque is equal to perpendicular force times distance. Now, the perpendicular force is going to be a tension. Perpendicular to what, though? Perpendicular to the radius. Radius is the lever distance. So force times distance for a pulley is usually almost always going to be tension times radius. Tension is the perpendicular force. The radius is the distance. So this torque, opposing torque, would be tension 1 times the radius, and the causing torque would be tension 2 times the radius. Okay, so we have all that squared away. Now, let's see what we have going on here. Well, we have a couple other things that we have to account for as well. Get to those in a minute. So we're going to use the torque on the pulleys. We did that. Newton's second law on the masses. We did that. And, all right. So another thing that's helpful to remember how there is a connection between linear translational variables equal the radius times the angular variables. And we had 3 such equations. We had S is equal to R theta. We had V was equal to R omega. And we had A is equal to R alpha. Well, we're going to use this one right here. Solving for alpha, we get A divided by R. We're going to need this. We're going to have to substitute with that later on. You'll see what I mean in just a moment. Okay, so first, let's go Newton's second law for each mass. Okay, I'm going to start with little m. Little m is accelerating upward. So you've got T1 minus mg equals little ma. Okay, and you also have m2, which is accelerating downwards, and that's big mg minus T2 equals big ma. Your last step is to use rotational Newton's second law and that's net torque equals I alpha. Well, your net torque is your causing torque minus your opposing torque equals I alpha. But here's what we're going to do with that. We're going to go, causing torque was tension 2 times radius minus the opposing torque, which was tension 1 times radius, equals I alpha. Now, what was I? I was this value here, K M, K M mass of the pulley, R squared. All that is I, times alpha. But now is where I'm going to substitute for alpha. What is alpha? It's A over R. So what we do with this net torque equals I alpha equation is we substitute translational variables for it. And what that allows you to do is cancel all the R's. Watch. This cancels with one of those, and then you're left with one factor of R in each term. Now, what are we left with? T2 minus T1 equals K times mass of the pulley times A. Okay, so at this point, we have all three equations, and what we're basically going to do is we're going to take the first equation, solve it for T1, plug that value in here. Then we're going to take the second equation, solve it for T2, plug that value in here. Then when it's all said and done, we're going to isolate our variables, get all the accelerations together, and we will solve for A. Let's do this. Let's figure this out. Okay, let me go over here to figure this out. So this one here, the first equation, I would have to add little mg, and I get T1 is equal to little mg plus little ma. This one here, I would have to add T2 over to this side and subtract ma over to that side. And so T2 is equal to big mg minus big ma. Those are your two values for T1 and T2. So we'll start with T2. Big mg minus big ma minus, right, your value for T1, which is little mg plus little ma. And all that's equal to K times mass of the pulley times A. Now you can see you've got ma terms in three spots. You've got to get all those together on one side and get everything else over on the other side. So here's what I'm thinking. We don't really need the parentheses so much anymore. Oh yeah, we do. We need to distribute the negative on that second one. So let's rewrite this one more time. Big mg minus big ma minus little mg minus little ma. And that's equal to K MPA. I'm going to add ma to this side, and I'm going to add little ma onto that side. And so we have big mg minus little mg equals big ma plus little ma plus K MPA. I am now going to factor out my a's and divide away those masses. So factoring out my a's, I have big mg minus little mg equals big M plus little m plus K times the mass of the pulley, all divided by A, divide by the sum of those masses, and we got it. There we go. Okay, example 2. Now the mass, a smaller mass, rests on a table whose coefficient of friction is mu. String passes over a small mass over the same pulley to a large mass, which is hanging over the edge of the table. Draw the forces acting on the masses and the pulley and determine the acceleration of the system of masses. Okay, so let's start with little guy here on the table. You know you've got normal force up, you've got tension going this way. I'll call it tension 1 since it's the first tension we're referencing. I have little mg, the weight going down, and we have sliding friction. Since the system is accelerating, that friction must be kinetic friction because you are moving. Well, focusing on the big M, we've got big mg, and you've got the other tension, the other side, which we'll call tension 2. Now we know tension 2 pulls down on the radius of the pulley that way, and tension 1 pulls on the pulley that way. Okay. Tension 2 is the causing torque. Tension 1 is the opposing torque because the whole pulley will rotate in the clockwise direction once the system gets going. Right, so torque 1 will be tension 1 times radius. Causing torque will be tension 2 times the radius. Again, we're using forces and torques. So let's start off with little m1. Start off with little m. So little m, you've got your net force equals ma. So your net force, your causing force would be tension 1 minus friction. But friction is mu times normal force, and that is equal to ma. Now, substitute for normal force, and we know that T1 minus mu mg equals ma. I'm going to add mu mg over to the other side. We have tension 1 is equal to mu mg plus ma. Okay, there's that. Now, let's focus on big M. Big M is accelerating downward. So you've got big mg is the causing force minus tension 2 is equal to big ma. I'm going to add T2 to this side, subtract ma to that side, and T2 is equal to big mg minus big ma. That over here. Okay, so we have those. Now, last step, we're going to use rotational. Rotational Newton's second law is just net torque equals I alpha. Okay, which is causing torque. The causing torque is tension 2 times radius minus the opposing torque, which is tension 1 times the radius, is equal to, you can see what the I is there, it's K MPR squared times alpha, which is A over R. Remember the substitution. We substitute for I, substitute for alpha. Cancels, 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 cancels. And we have T2 minus T1 equals K MPA. All right, at this point, let's substitute this value right there for T1, and let's substitute that value right there for T2. So T2 is going to be big mg minus ma, and then minus T1 is going to be mu mg plus ma is equal to K MPA. And now we've got our all three equations here. What I'm going to do now is I'm going to distribute the negative and then rearrange the MAs. So we've got mg minus ma minus salut mu mg minus little ma equals K MPA. MPA. Let's go ahead and add the MA over to this side, add the little MA over to that side. And when we rewrite this, we get big MG minus mu MG is equal to big MA plus little MA plus K MPA. Again, factor out the A's, divide away the rest of the masses. And we have big MG minus mu little mg. It's going to be divided by the sum of the masses, big M plus little m plus K times m sub p. You could factor out a G if you want to, but I'm not going to. Section 9.5, rotational energy. Objects that rotate have rotational kinetic energy. And the equation for that is K, the rotational kinetic energy, is 1/2 I omega squared. That's also easy to figure out too. These are the variables we translate bit by bit. So your translational variables, and then these are your rotational variables. So you already know X translates into theta, V translates into omega, A translates into alpha. But we've seen a few others. Force translates into torque. Mass translates into I, the rotational inertia. And so now we can use that if translational KT, translational kinetic energy, is 1/2 mv squared. That means rotational kinetic energy is 1/2 I omega squared. That's exactly what we have right here. So it's a very easy equation to remember if we remember how the translational variables convert and translate into rotational variables. Okay, when finding gravitational potential energy of an object, the object's height should be measured to the center of mass of the object. Okay. So in this example, we have a heavy block of 3 kilograms is attached to a rod of mass m and length 2 meters. The end of the rod is not attached to the block. It is pivoted on an axis to form a physical pendulum. The assembly is displaced and the angle of 37 degrees relative to the vertical and released. Determine the speed of the block as the assembly passes through the vertical. Well, first, let's find the total rotational inertia of the block-rod combination. Okay. Realize that this is going to be a conservation of energy problem when it's all said and done. So, the total rotational inertia of the block would be as follows. Let's treat the block as a particle that is rotating about that point right there. Okay, particles are point masses, and point masses have so I of the block would just be mr squared. Now, I of the rod, well, see, that's different because the rod is rotating about the endpoint. And the rotational inertia of the rod about the endpoint is 1/3 ml squared. But if you think about it, L is really the radius of this circle. So I'm just going to actually rewrite this as 1/3 mr squared. So 1/3 mr squared plus mr squared, that means the rotational inertia of the system would be 4/3 mr squared. Okay, and we can actually figure out what the numerical value is for later on, just to make the math a little easier when we get to it. 4/3, the mass was 3 kilograms, the radius was the length of the rod, which is 2 meters, and we have to square that. So that cancels. 2 squared is 4, times 4 would be 16, and the units are kilograms meter squared. Okay, now, since this is a conservation of energy problem, we need to figure out what the height is, because you're talking about potential energy, which is mgh, converting into kinetic energy, which is 1/2 I omega squared at the bottom. Okay, and then we'll change the omega into speed, into translational speed v. You'll see how we do that in a moment. So remember, gravitational potential energy is involved here. We need to take it from the center of mass, not the bottom of the problem. So the center of mass is, well, we have a couple different things. The center of mass is going to be so we're going to use conservation of energy to solve this, and that's going to tell us that the energy initial at the top is equal to the energy final at the bottom, which is really going to be mgh. And I'm going to rewrite this as kind of a big M GH, because that's really going to be the combined mass of everything, okay? But mg, it's going to relate to the center of mass. M is not just the total mass, it's the center of mass, which not quite at the middle. It's going to be, probably a little bit closer to the end right there, but we'll be able to figure it out. Okay, I'll show you how to figure that out in a second. So you got big mgh equals not 1/2 mv squared, but 1/2 I omega squared. Okay, and we'll be substituting for I and omega squared shortly, but for now, what we need to do is we need to figure out how we're going to substitute for some of these variables. Okay, so the first thing I'm going to tell you is h. Okay, let's figure out how we can substitute for this. Okay. Now, the first thing I'm going to tell you about h is, and this is the height of the block, okay, that little height right there. So L is the entire length of the pendulum, and the pendulum is going to go all the way down here too, which makes that the adjacent side of L, or L cosine theta. So the height is equal to L minus L cosine theta. Okay, and we're going to need that. Or I'll factor out an L, and the height is equal to L times the quantity of 1 minus cosine theta. Okay, so we'll need that. Now, the other thing we need to do is we need to kind of figure out what's going on with this. It's not just the gravitational potential energy of the rod, it's the gravitational potential energy of the rod block system. We found the total rotational inertia of the system. We should figure out the total, figure out what that is, that mgh, okay? Because it's not going to be just mgh. So here's how we can figure it out. The potential energy is going to be the potential energy of the block plus the potential energy of the rod. Okay, now the potential energy of the block, that one's going to be mgh. And we already told you h is the L times the quantity 1 minus cosine theta. Okay, but it's just got mgh. The rod, on the other hand, we're taking it from the center of mass of the rod, and it's going to be L over 2 is the halfway point. And that's exactly where it's going to get to over here is L over 2. So it would be M times G times H over 2. Okay, because it's half of it. So MGH plus MGH over 2 is 3 halves MGH. That is the potential energy for the system. Okay, so we'll need that. Okay, so here we go. I'm going to take this all down here. So in place of potential energy, I'm not going to write it that way. I'm going to write 3 halves mgh, but instead of h, I'm going to write the equivalent for h, which is L times the quantity of 1 minus cosine theta. So all of that is our potential energy of the system. And that's going to equal the kinetic energy, which is rotational kinetic energy, against 1/2 I omega squared. Now, at this point, you need to substitute for I, and you need to substitute for omega squared. Well, I, we figured it out already. It's 16. We'll plug in for that in a minute. But actually, I'm going to leave it as 4/3 mr squared. I'll show you why in a moment. I'm going to leave it symbolic. So I'm going to substitute for I, and I'm going to substitute for omega squared. Recall that V is equal to R omega. That means omega is equal to V over R. And if omega is equal to V over R, square everything, omega squared is equal to V squared over R squared. So I'm going to substitute for I and omega squared. And I get 3 halves mgl times the quantity of 1 minus cosine theta. And that's going to equal 1/2. Okay, now I is 4/3 mr squared. Okay, and then we're going to substitute omega squared for V squared over R squared. Now, notice all the things that cancel. R squared cancels with R squared. Let's see. 2 goes into 4 2 times, and we are left with 2/3. Okay. I'll leave that part of it out of it for a second. Here's why. Okay, so I can cancel out the 1/2 on both sides. There we are. Okay. So now I have 3 mgl times the quantity of 1 minus cosine theta, and that's equal to 4/3 mv squared, because that's all that's left, mv squared. Okay, I'm going to multiply both sides by 3/4. Okay, and at this point, and I'll cancel mass on both sides. And then I can square root. Okay, so what I have is I have V is equal to the square root of 9/4 times GL times the quantity of 1 minus cosine theta. And you should be able to plug in from there. 9/4 times 10 times the length of 2 times 1 minus cosine of, it was 37 degrees. Okay, we get approximately about 9.06, about 3 meters per second would be the translational speed at the end of the rod. Section 9.6, rolling objects. When an object rotates, it has both translational and rotational energy. There are two types of rolling: rolling with slipping and rolling without slipping. So, equations you can use while rolling without slipping. Well, what's going on? You have translational kinetic energy, which is 1/2 mv squared, because as a wheel rotates like this, the center of mass moves from one spot to another spot. But the wheel is also rotating at the same time, so you also have 1/2 I omega squared. You have both of them, okay? Now, if you're gliding and you're not actually rotating, then all you have is translational kinetic energy. If you're just pure rotation with no translational movement whatsoever, in other words, the object did not move from point A to point B, then all you have is rotation. But if you're rolling without slipping, your center of mass is moving, your center of mass is translating, and the object's rotating. So you got a little bit of both. Okay, now, the other thing we can also use is something to consider. If the translational speed is greater than r omega, then the object is going to translate more than it rotates. The opposite is true. If the translational speed is less than r omega, then there's more rotation than translation. Okay, so we can use both equations at the same time if rolling without slipping, right? But the static friction has to be a maximum, meaning there's no other values of static friction. It's just the max static friction. Friction only removes mechanical energy from the object if it slips. So if it slips and it skids on a surface, then you've got mechanical energy lost due to friction. Otherwise, friction causes a torque to make the wheel rotate. An object that rolls without slipping actually rotates instantaneously about contact points with the surface. This is because a circle is a polygon with an infinite number of sides. And if the polygon were to roll, it would merely rotate about each point in contact with the surface. So consider an object rolling without slipping up an incline, then down an incline. Draw the forces acting on the object as it rolls in both directions. Let the force be the start to where the force is applied. Well, recall that although torque is a perpendicular force times distance, the first way we defined it was r cross f, where r is the, not necessarily the radius, but it's the lever distance, and F is the perpendicular force to that lever. Now, we're going to use this to help figure out the direction of friction. Sometimes friction goes along with the roll, sometimes it goes against the roll. Okay, and the way to figure it out is the following. Realize that friction is what causes torque on a rolling object. Now, the friction, like I said, either goes with the rolling object or against the rolling object. How do we figure this out? Well, first thing we know is torque and angular acceleration always have to go together. Those vectors always point the same way. Now, the first point would be if your wheel or your rolling object is speeding up. That means torque and alpha are going the same way as the rotational rate of omega, the spin. Whichever way it's rotating, that's the way torque and alpha go. if your object is slowing down. The torque and the angular acceleration go opposite direction too. So now to figure this out, we need to use what is called the right hand rule, RHR for short. Here's how the right hand rule works. Okay, so let's say you have a surface, and let's call this a big rolling object. Okay, and let's say it's rotating this way. Now what you do is you put your fingers, and this is called right hand rule for a reason, you have to use your right hand. You put your fingers in the direction of the curl. See how the rotation is curling in the counterclockwise direction? Well, you put your fingers in the direction of the curl, and your thumb goes in the direction of omega. The angular velocity is actually perpendicular to the actual rotation. Okay, if the wheel were spinning the other way, counterclockwise, we'd put our fingers clockwise with the rotation, and our thumb would be in the direction of the angular velocity. So your torque, angular acceleration, and omega, all three are going to actually be perpendicular to the rotation. Okay, back to friction. So we have the weight, we have the normal force, and the problem is sometimes we have friction going with rotation and sometimes it's going against rotation. Let's figure this out. Okay, if the object is speeding up, so say we're going this way, but we're going faster, that means that if I put my finger in the direction of curl, omega is out of the page. But so is torque and angular acceleration, alpha. They're all out of the page. So what I do is I then put my thumb representing torque out of the page. I go R, the radius, cross F, and my fingers are pointing, the tips of my fingers are pointing in the direction of force, which in this case is friction. And you can see it's pointing that way. Now, what if the object were going slower? Okay, it's still rotating this way, but if it's going slower as it's rotating that way, that means even though omega is going this way, the actual spin is going this way, when you slow down, the angular acceleration always goes opposite velocity. So velocity, the angular velocity is out of the page relating to this counterclockwise rotation, but the angular acceleration and thus the torque are going into the page. Okay, now follow the logic here. We're going to go R straight down. Kind of hard for me to show this. Breaking my wrist showing this. We're going to go R straight down, cross F. That puts my fingertips going forward. Try this one more time. Okay, so I'm going to go into the page. There we go. So thumb is into the page, acceleration, angular acceleration, torque are into the page. I'm going to go R straight down to the surface, cross F, and you can see F, the friction force, is going this way, in the direction of rotation, in the direction of motion. So figuring out the direction of friction takes a little bit of right-hand rule and a little bit of processing whether or not the object is speeding up or slowing down. Okay, let's figure out the forces acting on this. So you've got the weight going down, you've got the normal force going perpendicular. But how about that friction? Well, if I'm going up an incline, most likely I am slowing down. Okay? Now, what that means is omega might be spinning in the counterclockwise direction. But if I'm slowing down, that means alpha is actually spinning. Alpha is going against. So if alpha is going against, I would put my fingers in the clockwise direction. And by doing that, my thumb would be going into the page. And if my thumb is going into the page for angular acceleration, torque is also going into the page. So I put my thumb into the page, put my fingers, I'm going to zoom in on this right here. My fingers would go R, cross F, and that puts friction going up the plane. This was the important part of that right there. Okay, now let's focus on this one here. We're going downhill. Still have normal force. Still have weight. None of that changed. But what about friction? Well, if I'm going downhill, I am most likely speeding up. And if I'm speeding up, omega, you can see, is spinning in the clockwise direction. So is alpha. So is torque. Okay, so that means put your fingers in the clockwise direction. Your thumb goes into the page. Keep your thumb into the page for torque, and torque is equal to R cross F. So we're going to go R, your thumb's into the page. We're going to go R, it's too big there, R cross F. And in both cases, friction is going up the plane. Okay. Now, going back to the first example, what if the object were being launched up the hill, and let's say this ball had a little motor of its own and it was going faster and faster, not slower and slower? What if it were going faster? Well, if it was going faster, that would mean that alpha would be in the same direction as omega. That would put your thumb out of the page for angular acceleration and torque. And that would, when you do torque equals R cross F, R, bend your fingers, cross F. That would put friction going down the page. So in order to figure out the direction of friction, you really need to know whether the object is speeding up or slowing down as it rolls. That is a huge, huge point. Okay, so now if I have nothing but pure rotation, if I'm rolling with no translation, then all I have is just pure rotation, nothing more. No translational velocity, I'm just spinning. If I'm rolling and translating, it means I have a little bit of translational speed and some rotational velocity. If I'm rolling without slipping, then that means this is the fastest speed I'm going to have, maximum speed, and then this is going to be the largest spin rate I can go to. But I've got a little bit of both as well. Okay, so let's take a look at example 1 here. Okay, we have a wheel of mass m, radius 0.25, and moment of inertia I equals 1/2 mr squared, is held just above the table and spun to an angular velocity of 30 radians per second. That would be right here. At time equals 0, the wheel is released and it lands on the table without bouncing. As the wheels spin, it translates from pure rotation through rolling with slipping to rolling without slipping. The coefficient of friction on the table is 0.2. first, let's determine the acceleration of the wheel. Okay, now the only unbalanced force that's acting on that thing is friction. Friction is the thing that causes acceleration. So I'm going to use net force equals ma, causing force minus opposing force equals ma, which would be friction. Kinetic friction equals ma. Okay, now substitute. Friction was mu times normal force. That equals ma, but normal force is mg. So it's mu mg equals ma. Masses cancel, and a is equal to mu times g. Okay, oh, let me plug in numbers, sorry. I forgot we had numbers here. Okay, so mu is 0.2 times 10, which means the acceleration is about 2 meters per second squared. Okay. Let's see. Write an expression for the linear velocity of the wheel as a function of time. Okay, well, v equals v naught plus at. We'll take care of that. That's velocity as a function of time. The initial translational velocity is 0, and so v is equal to a times t, or 2 meters per second squared, times t. And so we could just say v equals 2t would be our function. Velocity is a function of time. Okay. Determine the angular acceleration of the wheel. Well, kinetic friction is providing the only torque here. So we're going to use rotational Newton's second law to figure this one out. So you've got net torque equals I alpha on this one, which is causing torque minus opposing torque equals I alpha. There is no opposing torque. The causing torque is only due to friction. Okay, so recall torque is equal to the perpendicular force times distance, which would be friction times the radius. The radius would be that lever distance. So we've got friction times radius equals I, but we were told that I is 1/2 mr squared. So I'm going to substitute 1/2 mr squared. And in place of a, no, I want to solve for a. Okay, so friction, let's see, the radius cancels on one side. I'm going to go ahead and multiply by 2. And we can see that, I can substitute for friction. Friction would be mu times normal force, or mu mg, and that's going to equal to 1/2 m r alpha. The m's will cancel, and alpha would be 2 times mu times g over r. So 2 times 0.2 times 10 divided by r, which is, 0.25. Okay. So we have 0.2 times 10 is 2, times 2 is 4, and 4 divided by 1/4 is really 4 times 4, or 16 radians per second squared. Okay, write an expression for the angular velocity of the wheel as a function of time. Well, in this one, we're going to use omega equals omega naught plus alpha t. Now, there actually is an initial omega naught because the wheel was spinning before it dropped on the surface. So omega would be 30 radians per second minus, plus your alpha t, which was 2 mu g over r times t. Okay, now, uh, okay, so because the wheel as it's rolling is going to be slowing down slightly as it rolls, that's going to be negative alpha right there. So omega is equal to 30 minus, and the alpha we came up with was 16t. Okay. At what time t does the wheel begin to roll without slipping? Okay. Slipping occurs when v equals r omega. Not when v is greater or less than r omega, but when v equals r omega. So v was mu times g times t. Okay, because I'm going to go back. Remember what the acceleration was. The acceleration was mu g. So I'm plugging mu g times t. A times t equals r omega. And omega was the 30 minus 16 t. Okay, let's go ahead and distribute that through. We have mu gt equals 30r minus 16 RT. At this point, go ahead and add those together. We're going to factor out a t. So we get 16 RT plus mu gt equals 30r. Go ahead and factor out a t and divide away the leftover. And you have 30r over, now if you factor out a t, what was left over that you divided was 16r plus mu g. Or it's 30 times 0.25 over 16 times 0.25 plus 0.2 times 10. There we go. So we have about 7.5 over 4 plus 2. Okay, so 7.5 over 6, about 1.25 seconds. So at 1.25 seconds is when the translational velocity equals the r omega. Okay, example 2. An object of mass m, radius r, and moment of inertia I equals k mr squared rolls from rest at the top of an incline h, length x, and angle theta. The coefficient of friction with the incline is mu, which is high enough to prevent the object from slipping. Determine the linear velocity when it reaches the bottom. Okay. So there's a couple ways of going about doing this. So if we were to use conservation of energy, we could get this problem done pretty quickly. That's not the way we're expecting to do the problem later on. Okay, so first of all, determine linear velocity. Let's use conservation of energy. Okay, let's figure that out. At the top, energy initial at the top would be just mgh. Energy at the bottom finally would be, it'd be a combination. It'd be 1/2 mv squared, because the center of mass is translating itself downhill, plus 1/2 I omega squared. It's a little both. Okay. Remember, you have to substitute for I and for omega. So recall that I is equal to k mr squared, and that v squared over r squared substitutes for omega squared. So we're going to be substituting that. So let's go ahead and figure this out. We have mgh at the top is equal to 1/2 mv squared at the bottom plus 1/2, and let's do some substitution for I and for omega squared. So I is k mr squared times omega squared, which was v squared over r squared. Well, the r squared's canceled. We get mgh equals 1/2 mv squared plus 1/2 k mv squared. Well, I can factor out a 1/2 mv squared from both terms. And if I do that, I get mgh equals, factoring out the 1/2 mv squared, I'm left with 1 plus k left over. Okay, now I need to essentially solve this equation for v. So to solve for v, I'm going to multiply by 2, and then I'm divide by the 1 plus k. So v is equal to the square root of 2 mgh. Oh, and the mass is canceled right there. So 2gh over the 1 plus k that you divide over both sides. Now, check the list of variables. I can use h, I can always use g, and k is part of the moment of inertia, so that works as well. Okay, determine the linear acceleration at the bottom of the incline. Well, the forces acting on this would be mg, normal force, and if you're speeding up, that puts r cross f, friction is going up the hill. Mg sine theta is going downhill. So we do know that net force equals ma, which would be mg sine theta minus friction equals ma. Okay, but herein lies the problem. Let's see. I see. See, we don't know what the force of friction is yet. So doing it this way won't help us just yet. We need this, but we'll use that for the next part of the problem. Okay, but here, determine the linear acceleration. Well, let's use kinematics. V squared equals V naught squared plus 2ax. Okay, and we're solving for a. So starting from rest, a is equal to, well, another way to do it would be v squared. Remember, if this is v, right, then v squared, we just square both sides, it's 2gh over 1 plus k. So I'm going to substitute for v squared, it's 2gh over 1 plus k equals 2ax. The 2's cancel, multiply both sides by x, and okay. Now let's not forget to change the h. The h itself is, let me see. Yeah, okay, so the height, so the height is the opposite side of things, and that would be the x times the sine of theta. So it's gx sine theta over 1 plus k equals a times x. And you can see the x's are going to drop out too. And so a is equal to g sine theta over 1 plus k. Determine the force of friction as rolled downhill. Now use your Newton's second law. Okay, so we have mg sine minus friction equals ma. And you got your a. So I'm going to add friction and then subtract ma. And so friction is equal to mg sine theta going downhill minus m times that big thing right there, g sine theta over 1 plus k. There's your a. And at this point, let's just double check. We're good with mass. I mean, I could factor out an mg sine theta from both terms, and it's mg sine theta times 1 minus 1 over 1 plus k. I could do that. But there's no real need to simplify it more than it already is, as long as the variable's isolated and the other variables are the correct in terms of what you're supposed to write it as. Okay, so now suppose mu is small enough so that the object slips as it rolls down the incline. Determine the acceleration as it falls. Okay, so we're going to use Newton's second law again. So causing force minus opposing force equals ma, which would be mg sine going downhill minus friction equals ma. Now, at this point, let's see. It's mu, friction is mu times normal force, right? And the normal force, go back up to the picture, the normal force balances mg cosine going into the plane. So this is really mg sine minus mu mg cosine. equals ma. Masses drop out everywhere. And a is equal to g sine theta minus mu g cosine theta. Okay, to determine the angular acceleration the object will have, we're going to use the net torque equals I alpha. Rotational Newton's second law. All right, we're solving for alpha. So the torque is going to be force times distance force is friction times distance equals I alpha. Now the force, the friction force, is mu mg times the cosine of the angle times the distance, which is radius r. That's going to be equal to k m r squared, that's I, times alpha. And you're solving this thing for alpha. Okay, now one factor of r will cancel on both sides. That makes it a little easy. And m cancels on both sides as well. So it looks like we just need to divide by kr and we'll get alpha by itself. So we have mu g cosine theta over the kr that we have to divide both sides by. Let's see. What is the minimum value of mu that is needed to cause the object to roll without slipping? Okay. Well, under these conditions, not only is V equal to, not only is V equal to R omega, but A is also equal to R alpha. So let me start there. A is equal to R alpha. A is G. Now I'm going to factor out a G in both terms here. So G times the quantity of sine theta minus mu cosine theta equals R times alpha, which we just saw was mu G times cosine theta all over K times R. And a lot of stuff's going to cancel here. So cancels, mu G cancels. Okay, got all that. Now, we are left with mu over K cosine equals sine minus mu cosine. All right, and it looks like we're just solving for mu. So to solve for mu, we're going to, let's see, okay, let's bring the mu's together like that, and then I'll factor it out. So if I factor out the mu, then I am left with, actually I can factor out a mu cosine theta. That's common to both terms. I'm left with a 1 plus 1 over k. That's left over. Okay, and that's going to be equal to the sine theta that's left over. So we're going to divide by have sine theta over cosine theta times 1 over 1 plus 1 over k. Okay, and yes, sine divided by cosine is tangent, so you could technically write this as tan theta over 1 plus 1 over k. Okay, but I think you'd be okay writing it like this as well. Okay. Section 10.1, 10.2, 10.3, and 10.4 involve the concept of angular momentum by itself and with collisions involving rotation. So momentum is a quantity that is conserved in a system if no external forces act on the system. Well, angular momentum is a quantity that is conserved in the system if there are no net torques. Angular momentum must be taken about point P in space. The angular momentum of an object depends on the point chosen, but regardless of the point, the angular momentum of the entire system is conserved about it. Okay, so you have an object, a mass, particle M, and it's moving in this direction right here. Okay, and relative to point P, you need the perpendicular component to that radius vector. That radius there really represents the the distance from the particle. The perpendicular component of that would be r perpendicular, or r sine theta. Now, for regular momentum, okay, for regular momentum, we have P is equal to mv. Now, break this down. That means P translates into L. L is angular momentum. Mass corresponds to I, the rotational inertia, and V corresponds to omega. So the angular momentum of a solid object about a point on its axis is L is equal to I omega. Okay, but what's the angular momentum of a point mass? Well, we can derive this one by going L is equal to I omega. Recall that I for a point mass is equal to mr squared, and that omega is equal to V over r. So we have mr squared in place of I, and we have V over r. Cancels, and we have mv r. So instead of just mv, like regular momentum, it's mv times that distance right there. Okay. Let's see. Oh, another thing to consider, right? L is going to be r cross P, the regular momentum, mv, which would be r cross mv, which is the same thing as using the perpendicular component, or mvr sine theta. Now in example 1, it says a student uses the apparatus shown to whirl a bob of mass m on the end of a string in a circle of radius r with angular velocity omega. Determine the following. The moment of inertia of the bob at the end of the string. Well, it represents, the bob at the end of the string represents a particle moving around some fixed point, which means I naught is equal to mr squared. What's the angular momentum of the bob? Well, the angular momentum of the bob, L naught, is equal to I naught omega naught. Substituting, it would be mr squared times omega naught. And that's exactly what it is. mr squared omega naught. The kinetic energy of the bob is not 1/2 mv squared, it's 1/2 I omega squared, which would be 1/2, and then I, we're going to replace mr squared, and then omega squared okay, and so the kinetic energy is 1/2 mr squared omega squared. Okay, so the student pulls the string so that the radius is slowly decreased to 1/3. Explain why the angular momentum still remains constant. Well, the only forces, gravity and tension, have no components tangent to the axis, so they exert no torque. And if there is no net torque acting on the system, angular momentum is conserved, remains constant. But let's figure out the new rotational inertia. So now the radius is, I'm going to call this r prime, is now the old radius divided by 3. So if I is equal to mr squared, then I prime, I guess we'll call it, is equal to m times the new r, which is r over 3 squared. That means I prime is equal to mr squared over 9. Now, mr squared is I naught, so it's the same thing as I prime is the same thing as saying I naught over 9. Determine the new kinetic energy in terms of that. Well, we'll call it kinetic energy prime. That's going to be equal to 1/2 times I omega squared. But that's 1/2 times our new I, which is I naught over 9, times our new omega squared. Now what's going on with the omega? Well, this is how conservation of angular momentum works. If the angular momentum remains constant, that means L initial equals L final, or I omega equals I omega. So if the radius drops by 3, then the rotational inertia drops by 9. Okay, that means omega increased by 9. So our new kinetic energy is 1/2 times I naught over 9, and then 9 squared would be 81 omega naught squared. Well, that goes into that 9 times. And rearranging this a little bit, I'll move that out front. It's 9 times 1/2 I naught omega naught squared. And that was the original kinetic energy that you had over here, because I naught was mr squared. So that means K naught is equal to 9 times the kinetic energy went up by 9. Example 2. A child of mass 60 kilograms runs at a speed of 2 meters per second towards a merry-go-round of mass 200 kilograms and radius 1.5 meters and moment of inertia 1/2 mr squared. The merry-go-round can freely rotate, but is initially at rest. A child jumps onto the edge of the merry-go-round and holds onto it, causing the merry-go-round to rotate at angular speed omega. This is essentially an inelastic collision. And as we learned about inelastic collisions, they're the type that the kinetic energy is not conserved, and there's a loss in kinetic energy after they collide. But visually, we kind of represented it very similar to two masses kind of sticking together after the collision. So if we have M1 V1 initial plus M2 V2 initial equals, well, the two masses stuck together, M1 plus M2 times V file or V prime. Okay, now we're going to be using conservation of angular momentum to figure this out, but we're going to need the combined rotational inertia. And so the total rotational inertia of the child merry-go-round system is going to be, now the merry-go-round itself has a rotational inertia of 1/2 mr squared because it's treated like a disk. The child, however, is a particle rotating about that middle point. So we're going to go 1/2 mr squared for the merry-go-round plus little mr squared for the child. Okay, plugging into those numbers, we have 1/2 times big M, which was 200, times, let's see, what was the radius, 1.5 squared, plus the child was 60 times 1.5 squared. And the rotational inertia of the system would be 225, yeah, but right, 225 plus 1.5 squared times 60 be about 135, which would be about 360 kilograms meters squared. Okay, we're going to need that and have that in our hip pocket. Okay, so conservation of angular momentum, L initial equals L final. Initially, not moving, only the child is. So we have M V naught R, that's the initial angular momentum of the child, equals I omega, but I is the I of the system because it's the child merry-go-round system that's rotating afterwards. And you're going to solve the thing for omega. Okay, so dividing by I, omega equals mv naught times r over I. So it's the mass of the child at 60 kilograms times the initial speed of 2 meters per second. The child is running beforehand, radius of 1.5 meters, all divided by I, which for the system we found to be 360 kilograms meters squared. And let's see, we have 2 times 1.5 would be 3. 3 times 60 is 180. 180 over 360 is 0.5. The units would be radians per second. Determine the kinetic energy lost during the collision. Well, you got to figure out the kinetic energy before and after to figure that out. So kinetic energy before is just due to the child, and it's 1/2 mv naught squared, or 1/2 times 60 times 2 squared. 2 squared is 4, half of 60 is 30, 4 times 30 is 120 joules. Afterwards, it's 1/2 I of the system times omega squared. So 1/2 times 360 for the system times omega squared, we found to be 0.5. So 0.5 squared is 0.25. A quarter of 360 is 90. Take half, we have 45 joules. And so the kinetic energy lost would be your 120 joules minus your 45 joules, or 75 joules. Okay, a little bit more on right-hand rule. You can see how it works there. Fingers curl in the direction of rotation, and the thumb points in the direction of all angular quantities. That would be angular momentum, angular velocity, even angular acceleration, and torque. All the vectors are perpendicular to the direction of rotation. Example 3. Consider two carts of mass m1 equals 10 kilograms and mass 2 equals 25 kilograms. Each car sports a rod that rises vertically out of the center. On M2, the rod acts as a frictionless pivot for a bar of mass 75 kilograms and length 2 meters. M1 is without a bar, but its rod is tall enough to strike the square bar if the carts are set on parallel tracks, as you see over here in the image to the left. Consider the following cases. In case 1, both carts are set on the same track as shown. The cart with no bar is moving toward the other with a speed of 20 meters per second. After the collision, the bottom car is at rest. This is a conservation of momentum problem, in that the momentum before the collision, I'll just write it as the momentum before the collision, I'm going to write as P initial equals the momentum after the collision, which I'll write as P final. Okay, how do we figure out how fast the top cart is moving after collision? Well, let's figure out what we have going on here. Initially, the momentum is only due to the first cart, and so it's m1 times v naught. But afterwards, the momentum is only with the bottom cart. But there's two masses on the bottom cart. There's the mass of the cart itself plus the mass of the bar, times the final speed in which it's traveling once it's hit. Because remember, this car stops after collision. Set those two equal to each other, and we have m1 v naught equals m2 plus m times v final. Solve for v final, and it's m1 v naught over m2 plus m, which would be 10 kilograms times 20 meters per second over 25 kilograms plus little m, which is 75 kilograms. Okay, that would be 200 over 100, which would be 2 meters per second. What is the angular velocity of the rod? Well, the angular velocity is 0 because the rod is not given a net torque in which to rotate. Therefore, it will not rotate. How much kinetic energy will be lost during the collision? Well, figure out the kinetic energy before and then after, and then subtract the two. So initially, it's 1/2 times m1 times v naught squared. So it's 1/2 times 10 times 20 squared. Now 20 squared is 400. 400 times 10 is 4,000. Take half of which we have 2,000 joules. Afterwards, it's 1/2 times m2 plus little m times v final squared, which would be 1/2 times 100 total kilograms of mass, and the speed was 2 meters per second squared afterwards. So 2 squared is 4, times 100 is 400, take half of that, it's 200. That means the kinetic energy lost would be 2,000 minus 200, or 1,800 joules. A lot of kinetic energy lost during this collision. Okay, little typo here. This should say case 2. Now in case 2, both carts are set on different tracks. The cart with no bar moves towards the other with a speed of v0, just like before, and strikes the very end of the bar right here. After the collision, the bottom cart comes to rest. So that means after collision, this cart is going to move forward and the bar is going to rotate. So you've got a couple different things going on here. Now, to figure out the actual speed of the top car, we can still use conservation momentum, which is initial momentum equals final momentum. Still use that. And it's really the same idea if you think about it, because you've got m1 v0 equals m2 plus m times v final, and v final, right, is still going to end up equaling 2 meters per second. So that really didn't change. However, this time you do have angular velocity afterwards. Okay, and we're going to use conservation of angular momentum for this one, which is L initial equals L final. L, now recall L is equal to either I omega or it's equal to mvr, depending if you're a particle or a rigid object rotating through an axis. Well, this cart represents a particle with respect to that point right there. And so before collision, Li, we have m1 v0 and then r. Okay, and it's going to be right here. What we want for r is really, we want the perpendicular component right here, this component right there, which you can see is half the length of the bar, L over 2. So that would be m1 v0 L over 2. Now final, what's going to happen afterwards is you're going to have rotation about the center. So afterwards, I omega, where I is 1/12 ml squared, right, times omega. That would be the rotational inertia of a rod rotating about its middle. Okay, we're going to set those two equal to each other. So L initial equals L final, which would be m1 v0 L over 2 equals 1/12 m. This one would be little m because it's the mass of the bar that's rotating, little m, times L squared, right? And then times omega. And then we have to solve for omega. So one factor of L you can see will cancel. So omega, we'd end up going to, let's see, 2 goes into that, 6 times, multiply both sides by 6, m1, v naught, over, and then we're going to divide by the ml right there in order to get omega by itself. Go ahead and plug into that. Times 10 kilograms times 20 over 75 times the 2. So that would be 60 times 20 is 1200 over 150. And that would comes out to 8 radians per second is the rate at which it's been rotating. Okay, kinetic energy lost during the collision, same idea. Kinetic energy initial is 1/2 times m1 times v naught squared, which is 1/2 times 10 times 20 squared, or 2,000 joules. Kinetic energy final, 1/2 times m2 plus m times v final squared, plus 1/2 I omega squared. Okay, plug into that. 1/2 times 100 kilograms times 2 meters per second squared, plus 1/2 times I. Did we figure out I? No, we didn't. Let's figure it out. So I is 1/12 ml squared. So it's 1/12 times 75 times 2 squared. Okay, 2 squared is 4 times 75 is 300. Divided by 12 is 25. So we have 25 kilograms meters per second. So 25 times and then 8 squared. So 2 squared is 4 times 400. That would be 200 plus. And then here we have 8 squared is 64 times 25 divided by 2 is 800 equals 1,000 joules. So kinetic energy lost (2,000 minus 1,000 equals 1,000 joules. Section 9.3, Parallel Axis Theorem. An object could be set on an axis that is not through the object's center of mass. In this case, the moment of inertia becomes greater and farther from the axis of the center of mass. So, say for instance, you have a disk that you're rotating through the center. Okay, well, the rotational inertia is the rotational inertia through the center of mass, because the center of mass is the center of the disk. But let's say we were to rotate it about that point right there. That would look like this. Kind of hard to do that, but you get the idea. This is our axis of rotation right now. And so when that happens, now I has a different, there's a different rotational inertia. So the way we figure it out is the total rotational inertia is going to be I through the center of mass, which would be if you were rotating it through the center of mass, in this case of a disk, plus md squared, where m is, of course, the mass of the geometric object, and d represents the distance from the center of mass to the new parallel axis. This is called parallel axis theorem because you're going to get a parallel axis to work. So let's make sure we understand this. I is the center of mass moment of inertia for whatever the geometry of that object is. M is obviously the mass, and d is the distance from the center of mass to the new parallel axis of rotation. Okay, let me show you an application of how to use parallel axis theorem. We were told that, I'll do this over here in the box, we were told that I for a rod at the end, so was 1/3 ml squared. And the rotational inertia for a rod about the middle is 1/12 ml squared. So how do we get that value about the endpoint? That's an application of parallel axis theorem. So the rod about the middle, that would be the center of mass, is this right here. If we use parallel axis theorem, I equals ICM plus MD squared. Rotating about the endpoint here makes this distance d. Distance d would be half the length of the rod. So I would be 1/12 ml squared. That would be the I through the center of mass, plus m times L over 2 squared. So we have 1/12 ml squared plus ml squared over 4. Let's get a common denominator going on here. This would be 1/12 ml squared plus, multiply both sides by 3/12 ml squared. Well, 1/12 plus 3/12 is 4/12 ml squared, which is 1/3 ml squared. So we get that value right there. In the following example, we have a uniform disk of mass m and radius r is pivoted about the point P. You can see at the very bottom of the disk rather than the middle of the disk, on the edge of the disk. Usually the center of the disk, or initially, the center of the disk is directly above the axis. When the disk is released, the center of the disk follows the path as shown, because the disk is going to rotate about that point right there. Determine the speed of the center of the disk when it reaches the lowest point. Well, since the disk is going to be falling like this, we're going to be using conservation of energy. But we also need to do a little parallel axis theorem work here, because you're not rotating about the center of the disk, you're rotating about the edge of the disk this time. So let's figure out the new rotational inertia first. I is equal to ICM plus MD squared. Well, the rotational inertia of a disk about its middle is 1/2 mr squared plus m times d squared, where d squared is r squared. So 1/2 plus 1 would be 2/2 is 3/2 mr squared. Okay. Also, recall that V is equal to R omega, so omega is equal to V over R. And if I square the left and right side, omega squared equals V squared over R squared. We'll need this one for substitution at a later time. All right, let's use our conservation of energy here. Energy initial. So energy initial with kinetic energy 0 to start with. Gravitational potential energy is mgh. And spring potential energy 0 because there's no spring in here. All right, so final energy. Kinetic energy final would be all rotational, because you're only rotating about that point right there. Gravitational potential energy would be 0, and the spring potential energy would be 0 because, again, there's no spring. Okay, the initial potential energy would be mg, and the height that it falls would be r plus r, or 2r, or 2 mgr. Energy initial equals energy final. That would be 2 mgr equals 1/2 I omega squared. So we have 2 mgr equals 1/2. We're going to replace I with 3/2 mr squared. And we're looking for the speed, not the angular speed, but the linear speed. So we're going to replace omega squared with v squared over r squared. Okay, in which case 2 mgr equals 3/4 mv squared. Masses cancel, multiply both sides by 4/3, and we get 8/3 gr, and just take the square root of that. Now consider a hoop of mass and radius subject to the same exact situation as the disk. When the center reaches the lowest point, will the hoop move faster or slower than the disk? Well, the hoop, has a greater mass distribution from the center, so it has a larger I. So if we use our logic from before, we have 2 mgr was the initial potential energy equals 1/2 I omega squared. The energy is the same, but the geometry is different. So I is greater, which means omega is going to be less. If omega is less, V is less, or should be. Okay, same potential energy, more moment of inertia, less omega, less velocity.